Hello, everybody. Our project name is Dolly. We're Group 31. My name is Uygar Baran. I'm a computer engineering student. I worked on the direction finding interfacing and main logic.
Hi everyone, my name is Jaime Borges, and I worked in the motor systems, distance sensing, and mechanical design and assembly.
Hello, everyone. My name is Jaquan Foy. I'm an electrical engineering student. I worked on a part selection and hardware design.
Hi, my name is Kristen Ling. I'm an electrical engineering student, and I also worked on the part selection, hardware design, and the assembly of the project.
What is Dolly? Dolly is an automatic platform dolly with four wheels that follows the dedicated user while carrying their load and maintaining a certain distance between the user and itself. Its 2 by 2 foot loading area allows users to put their loads on top of it. After users put their loads on top of Dolly, wherever the users move on foot, Dolly will follow them while carrying their loads. So why Dolly? The idea of Dolly was inspired from smart automatic luggages that follow their users. While we liked this idea, we realized that we could put our own twist into it and make it more flexible by integrating the functionality of automatic following into Smart Square platform. A square platform, unlike a luggage, could carry anything, even a luggage. Dolly is great for people with physical disabilities because it provides users with hands-free transportation. Additional potential applications consist of distributing Dolly to warehouses if the project gets scaled up when it comes to the weight Dolly can carry, or carrying household objects or day-to-day loads. If you have a heavy bag and you don't want to carry it around all day on foot, just place it on Dolly. Now you can walk anywhere and it will follow you. Plus, your friends will definitely think you're cool, so it's a win-win situation. What sets Dolly apart? First of all, Dolly is a simple and cheap solution to transporting objects hands-free. When looking at the competitors, we saw that their products were very complicated. They had fingerprint authorizations, functionalities that take care of very detailed edge cases. Essentially, they honed in on things that an average user might never use yet still have to pay. Dolly is created with simplicity in mind to provide the user with the best trade-off when it comes to money and main functionality. Dolly also is more flexible in being able to carry a wider range of items compared to, for example, a smart luggage, as mentioned in the previous slide. The second factor that sets Dolly apart is that Dolly uses an entirely local direction finding technology called angle of arrival. It doesn't have to communicate with external infrastructure such as satellites to be able to function. As long as you're within Bluetooth range of Dolly, it will work as intended. Dolly also is reliable both indoors and outdoors, unlike products that solely use GPS, since GPS isn't reliable indoors. Lastly, using Dolly will definitely spark new conversations with kind strangers along the way. Trust us, we can confirm from our experience testing it outside. Overall, Dolly is a simple, cheap, and flexible product that offers users hands-free transportation.
In order to implement this idea of an automatic following Dolly, our device will need two major functions. The first is a way to determine the direction of the user relative to our device. For this, we'll be using angle of arrival or AOA technology, which will be discussed further in the presentation. The second is a way of interpreting this direction data and automatically moving in that way.
There's multiple things we wanted to accomplish with Dolly, but there are three main things that we feel like we have to be able to accomplish. The first thing being, Dolly should be able to carry up to 20 pounds at a speed of 2-3 miles per hour. The up to 20 pounds is with what a person would averagely need help carrying. We think it's a good thing that Dolly would need to be able to carry up to 20 pounds. An average walking speed of a person is 2-3 miles per hour, so we need Dolly to be able to keep up with the user and not fall too far behind or just speed past the user. The second thing we wanted to accomplish was Dolly should be able to locate a user at a plus or minus 40-degree resolution at 80% accuracy. We want Dolly to be able to accurately find the user and be able to track the user to best of its possibility. So we want 80% as a good benchmark. The direction system we're using for Dolly is AOA technology. Direction data is then sent from the Bluetooth module to the main microcontroller. The main microcontroller sends commands to the motor controller to move in the appropriate directions.
You may be wondering why AOA was the direction-finding method of choice, since it's not a very well-known method. One of the main reasons that AOA is our method of choice is that it's completely local, meaning that the two devices, in this case the transmitter on the user and the receiver on Dolly, have direct communication with one another and do not need to rely on complicated networking or physical infrastructure like satellites or base stations. Being independent of physical infrastructure is important for having reliable performance indoors, which is the main environment that Dolly is going to be operated in. This is one major reason why GPS is not used in our design. Many people have also suggested using a similar method to the Apple AirTags or other similar location tags, but these tags rely heavily on having a large network of devices or tags, which is not accessible for a project like Dolly. Other RF solutions, such as radar, also have the benefit of being completely local, but have the downside of having to do additional computation to distinguish the user from other objects in the area. This would especially be problematic and complicated in environments with many objects and/or other people nearby. So AOA works by utilizing an antenna array. Basically, the user in our application would carry a Bluetooth beacon, and we could tell what direction the beacon or the user is in based on the time or phase difference of the received packet on the different antennas. The transmitter that's on the user is going to send something called a constant tone extension or a CTE packet. This is specific for the AOA protocol. And the receiver, which is on Dolly, is going to sample an IQ sample, which describes the current and the phase that's at the receiver. This will further be interpreted into the direction of the user.
Let's dive into the AOA communication between the tag and the antenna board. So, the communication roles are that the tag is a broadcaster while the antenna board is an observer. The communication process is as follows. Tag is constantly advertising itself while the antenna board is constantly listening for Scilab's tag advertisements. Once the tag advertisement is detected by the antenna board will process the tag advertisement accordingly. The tag's advertisement consists of Bluetooth signals with constant tone extensions appended to them. Constant tone extension is specific to AOA. It essentially is a certain tone or signal sent by the tag for a duration of time so that the antenna board, which has 16 antennas in this case, will sample this tone with each of its 16 antennas. Once the constant tone extension is sampled, it will be processed into an array of IQ samples, which then will be sent to the Raspberry Pi to be further processed. This process chain will happen constantly in real time. The overall AOA network consists of 4 components: the Silicon Labs tag, the Silicon Labs antenna board, a Raspberry Pi, and an STM32 CPU on our main PCB. The tag will be located on the user unless Dolly is used for other applications than intended. The antenna board, Raspberry Pi, and STM32 CPU will be located on Dolly. The tag communicates with the antenna board through Bluetooth as mentioned in the previous slide. The antenna board and Raspberry Pi communicate with each other through USB using the command response structure under Silicon Labs BG API. Raspberry Pi communicates with STM32 through UART. First, the tag's CTEs are sampled by the antenna board as IQ samples. Then, with the appropriate command of Raspberry Pi, these IQ samples are sent to the Raspberry Pi. Raspberry Pi then filters and converts these IQ samples into an angle, which represents the angle of tag relative to the antenna board. Raspberry Pi then transmits the angle to the STM32 CPU. This communication flow happens constantly in real time to provide real-time direction information to the STM32 CPU.
This slide shows our hardware block diagram for Dolly. Our main power supply will be a 12-volt battery, which will connect to 2 motor controllers and the PCB. The motor controllers will each independently control their own motor. The PCB will then feed the 12 volts into two different regulators. One is a 3.3 volt regulator and one is a 5 volt regulator. The 3.3 volt regulator will supply the STM32, our main microcontroller. The 5 volt regulator will supply the Raspberry Pi and the distance sensors. The distance sensors will connect to the STM32 through GPI opens. The Raspberry Pi will connect to the STM32 through UART. This will be where the Raspberry Pi gives the STM32 angle information for the direction finding. The Raspberry Pi will be connected to the Scilab's AOA evaluation kit through a USB cable. This connection will both supply 5 volts to the evaluation kit and will also be where the evaluation kit gives the Raspberry Pi data for computing the direction finding. The tag for the AOA kit will also be advertising Bluetooth signals to the AOA evaluation kit. This shows the schematic of Dolly. Most of it is digital, so it's pretty straightforward. This section is the main microcontroller. This is the power of Dolly, which is the battery input, the power switch, 2 voltage regulators, and some indicator LEDs. These are various headers to connect multiple sensors and the motors. And this is the header to connect the AOA breakout board. This slide clearly shows how all of our hardware will be connected to our custom PCB. The transmitting tag will be located on the user and will be constantly transmitting Bluetooth signals. The AOA evaluation kit will be receiving these signals and sampling them. Then it'll send these samples to the Raspberry Pi, and the samples will be used to calculate the angle that the user is in on the Raspberry Pi. These will be sent to the custom PCB through a UART line. The PCB will also be connected to distance sensors and motor controllers, and will take the direction of the user and the data from the distance sensors to control how the motor controllers should be moving the motors.
For the mechanical design of Dolly, we went with a custom build to maximize the compatibility with the selected hardware. The biggest structural decision had to do with the usage of wood, as a metal structure is more common on a robot. We ended up using a wood structure that is at 2 feet square due to the nature of the angle of arrival module. This is an RF-based direction finding method, so large amounts of metal wood needed to be avoided to reduce the interference between the module and the beacon. We also made sure that Dolly would have a low center of mass to keep the platform level on the ground when any movements would occur. Lastly, the differential drive setup on Dolly allows for rotation in place, forward and backward movement, or a combination of these two movements. We also made sure that 4 points of contact are always present by having 2 caster wheels on the back corners.
There are a couple trade-offs we had to consider. The first being battery lifetime versus max load. Motor requires a large amount of current, which is limiting since Dolly is a battery powered. Generally, more robust motors that could support a larger load require more current. Higher current draw means the battery will die faster. The second trade-off we had to consider was torque versus speed. Torque, which limits how much of a load Dolly could carry, and speed is inversely related. Motors must be geared appropriately to find the best balance of speed and maximum load.
To meet the requirements of carrying 20 pounds at 2 to 3 miles per hour, we had to look at 3 aspects of the mechanical design. We had to first make sure that each power wheel had enough friction between the ground and the wheel itself for the most effective transfer of torque. To accomplish this, we selected rubber wheels that were approximately an inch in width to maximize this transfer. Not only did we have to make sure the wheels had enough grip, but we also had to make sure that they were the right size and would go at the desired speed with the desired torque based on the motor and gearbox that we selected. We had to take into account the torque relationship that shows the wheel radius becoming smaller as the torque increases, but it comes at the expense of a lower rolling velocity. Since the selected motor can reach a maximum speed of up to 550 revolutions per minute, we could afford to select a smaller size wheel to maximize the torque. It is important to note that it took us a while to figure this out because we needed the exact amount of torque that had to be split between the three main components being the wheel, the gearbox, and the motor. For the motor type comparison, we compared three main types of motors. We compared stepper motors, brushed motors, and brushless motors. We had to rule out stepper motors because they have a low maximum velocity, which would mean that our dolly would not be able to meet our requirement of at least 2 mile an hour speed. And stepper motors have a high amount of torque, but as the rotational speed of this motor increases, the torque gets diminished. And lastly, between the brushed and brushless motor, they had mostly the same advantages and disadvantages. However, due to the fact that the brushless motor needs to have a feedback controller within it, it causes the price to be quite a bit higher. This means that a brushed motor was best for our application. When considering the motor, we had to make sure it had enough torque to move a reasonable load, be lightweight to minimize the initial weight of the dolly, and be affordable. We had three main motors to select from. However, the Daewoo gearhead motor fit best all the categories as it was affordable at $9, had excellent torque and speed figures, and was very light. It may sound odd that the selected motor comes with such a high torque figure. The truth is that it comes integrated with a worm gearbox that allows for a significant increase of torque. This is also greatly simplified our wheel selection as we had now our fixed torque and speed figures for the gearbox and the motor. We also had to consider the microcontroller that would handle Dolly's various tasks. We had to take a couple of things into consideration. We had to make sure that the chip was readily available. The chip also had to include communication methods such as UART and I2C, and it had to be able to generate our desired PWM signals. The STM32 best fit all of these requirements, the only downside being that it is an unfamiliar device for development for everyone in the group.
When searching around at different batteries, we wanted the battery we decided on to be able to accomplish a few things. We wanted it to be easy to buy, relatively cheap, be able to run our motors for a extended period of time. We wanted it to be rechargeable and be able to fit on dolly. We also wanted the battery to be able to go into airports if needed by the user. The battery we decided to go with was a lead acid battery. We saw that it was relatively easy to find anywhere and easy to get. We saw that it was cheap, and we saw that it would be able to get airport access. The things we were looking for in our regulator was it to be able to step down that 12 volt and to give us a minimum of a 3 volt output. We also wanted it to be affordable and in stock in case anything happens to it. We also be able to get more easily.
When it comes to distance sensor selection, we decided that per unit, it should be no more than $8, it should be easy to integrate, and be able to detect at least up to 3 meters. HCSR-04 ultrasonic distance sensor fits all the requirements and therefore is chosen to be integrated into Dolly. Dolly has 3 distance sensors spaced half an inch away from each other in front of Dolly to be able to detect the obstacles in front of it and come to a stop when necessary. We have decided to incorporate a Raspberry Pi into our design to handle the host application responsible for receiving IQ samples from the antenna board, converting them into angles, and sending them over to STM32 MCU on our main PCB. There are a couple reasons for this decision. Firstly, Silicon Labs' take on the AOA assumes that the antenna boards are stationary and are connected to central computers with operating systems. Unfortunately, due to this reason, Silicon Labs only provides example code that assumes the computer running the code has an operating system, and they do not have example codes that run on their own MCUs. This means that a significant amount of time is required to make their library work on an MCU that is not also made by them. Secondly, there's a lack of documentation when it comes to working with AOA libraries, as it is not a widely used technology. As a result, we have decided to integrate their libraries into an STM32 MCU as a secondary goal if time allows. This will provide us with the opportunity to utilize our limited time to improve the user experience of Dolly, which includes smooth turns and object detection. Therefore, we will be integrating the Raspberry Pi 4 Model B into our design. Lastly, we decided to go with the Raspberry Pi since we already have one on hand, and it is a small embedded computer which runs on a Linux-based operating system capable of handling Silicon Labs' real-time location library operations. Dolly state machine. Dolly has three states: stop state, turn state, and move state. After each state, Dolly checks if there is a tag advertisement detected because the tag is constantly transmitting new angle information of itself. When Dolly is initially turned on, it starts at stop state. At the stop state, Dolly stops the motors and checks whether a tag advertisement is detected. If not, then Dolly keeps going back to the beginning of the stop state. If a tag advertisement is detected, then Dolly checks whether it is facing the tag within a 40-degree beam width. If not, then Dolly enters turn state where it turns left or right based on which side the tag is located at. While Dolly is turning towards the tag, it keeps checking whether it is facing the tag or not and turns until it does face the tag. Once Dolly faces the tag, it lastly checks whether there is an obstacle within its stop range, which is 70 centimeters. If there is an obstacle within its stop range, then Dolly enters stop state. Note that this obstacle could be either a random object that's 1 cubic foot or more in volume or the user themselves. We want Dolly to stop in either scenarios. If there isn't an obstacle within Dolly's stop range, then Dolly enters move state where it starts moving towards the tag until either the tag is within its stop range or it is not facing the tag anymore. This state machine constantly runs in real time in order for Dolly to follow the user accurately. Examples of stationary and mobile Dolly. Dolly could be seen in the center of both small and big circles. The small circle indicates the idle range of Dolly. The big circle indicates the maximum detection range of Dolly. The area within the small and big circle is the moving range of Dolly. If tag number 1 is active, then Dolly would first turn towards tag number 1 and then would start moving forward towards it until tag number 1 is within the idle range of Dolly. Once it is, Dolly would stop. If tag number 2 is active, then Dolly would only turn towards tag number 2 to face it and then come to a stop, since it's already within its idle range. Lastly, if tag number 3 is active, Dolly would do nothing because tag number 3 is outside of Dolly's detection range. Dolly simply wouldn't even receive signals from tag number 3.
This slide shows a comprehensive breakdown of the expenditures that were incurred during the development and construction of Dolly. In the table in the right-hand side, we have marked the donated parts with an asterisk, as they are a significant factor in determining the overall team cost of constructing Dolly. Our total expenses amounted to $357, which would have been $638.25 without the generous contribution of the donated parts. Ultimately, we have estimated the cost of replicating Dolly at $529.25, which is substantially lower than our initial budget of $750. This achievement was made possible by carefully selecting the hardware components such as the motors and sensors, which proved to be pivotal in reducing the overall cost. Work distribution. Uyghur Baran was responsible for several key aspects of the project, including direction finding integration, device behavior state machine, system software integration, and the distance sensor and testing integration. Jaime Borges contributed to the mechanical design and actuator design, the housing assembly, and the device behavior and state machine, as well as anything related to the motor design and control and steering. Jacqueline Floyd was responsible for power-related research and part selection, as well as the selection and assembly of parts for the PVC and housing. He also contributed to the PCB design and assembly and the overall testing of the device. Lastly, Kristen Ling was responsible for the design of the PCB, selection of parts, the assembling of the PCB and housing, integrating hardware components, managing the project, and participating in device testing.